Today we're going to solve systems of nonlinear equations, and we're going to solve them both graphically and algebraically. So first, take a look at this system. Y equals the square root of x, and y equals 6 minus x. Hopefully you can recognize what shape the graph is going to be. Y equals the square root of x, goes through 0, 0, 1, 1, 4, 2, and it's a sideways curve like this. Now if you didn't recognize the shape of the graph, that's okay. All you have to do is make an XY table to get some values for the graph. And I will show you what that looks like as well. Because we're going to be taking the square root of x, I choose values that are perfect squares, like 0, 1, and 4. And then I simply substitute that in and get my y value. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Now if you're wondering why I'm not doing plus or minus 1, plus or minus 2, that's because in the given system of equations, this is defined as the positive square root. If it was supposed to be plus or minus, that would be written out front. The second equation, hopefully you recognize as linear. This is in slope-intercept form. If I rearrange it so the x term comes first, we can see that the slope is -1 and the y-intercept is 6. Again, if you didn't recognize that as linear, you can always make an xy table like we did for the first equation. I'm going to graph using the slope and y-intercept. So I go to 6. Remember the slope is -1, so that'll be down 1 over 1. I'm going to plot several points because look at that, I get to where they intersect. So from my graph, I can see that the solution to the system of equations is 4, 2. That point makes both equations true. When I solve this algebraically, so I'm going to pretend like I don't know what the solution is, I notice that both equations are solved for y. So I can use the substitution method. I can substitute root x in place of y. Another way to think about this is I can set them equal to each other. So here's the algebraic method. And now all I have to do is solve for x. Well, the square root would be nice if it wasn't there. So I'm going to square both sides. On this side of the equation, when I'm doing 6 minus x, quantity squared, remember that I'm doing 6 minus x times itself. So it's not just going to be 36 plus x squared. There's going to be an extra term in the middle. I have to use the distributive property to multiply this out. So I get x equals 36 minus 12x plus x squared. Now this is a quadratic equation, so in order to solve for x, I need to set it equal to 0. I'm going to subtract x over, and then when I write this down, I'm going to rearrange it so that it's in standard form. And now to solve a quadratic, we have a couple of options. We can factor, or complete the square, or use quadratic formula. I always like to try to factor first because it's pretty quick and simple. I'm looking for two numbers that multiply to a positive 36 and add to a negative 13. That would be -9 and -4. So x equals 9 and x equals 4. In order to get the solution to my system, I am going to substitute in the x value into both equations, or one of the equations, y equals root 9, y equals root 4, and so at 4 the solution is 2, and at 9 the solution is 3. Now according to our graph, you can see that we only have half of this curve, because in our original problem it was defined as positive root x. And so this solution here, 9, 3, if I look at the graph, would be over here. But this would be considered an extraneous solution. It's a solution that I get, but it's not applicable in the actual situation. So we only have one solution, 4, 2. Let's take a look at the next system. I'm going to graph first so I can see what's going on, and then we're going to solve it algebraically. All right, so my first equation, x squared minus y equals 4. I'm going to rearrange it so it's y equals. So I'm going to subtract over the x squared, and then I'll have to divide everything by -1, so I get a positive y. When you do that, you get x squared minus 4. Now hopefully you recognize this as a quadratic, and the minus 4 shifts everything down 4, and the parabola will open up. I am just going to make an xy table to find a few more points here. I'm going to choose 1. So I have 1 squared minus 4, which is -3. Mirror image over here, and let's put in 2. 2 squared minus 4 is 0. So 2, 0, mirror image, and my graph looks something like this. The second equation, hopefully you recognize as standard form of a linear equation. To solve standard form, you can use intercepts. So the x-intercept is where y equals 0. If I plug 0 in here, I see that x is equal to -2. Oh, look at that, -2, 0. The y-intercept is where x equals 0. So if I put 0 in here, I see y equals -2. 0, -2. So my second equation is a line, something like that. Now you can see we have two solutions here. We've got this one at -2, 0, and we have another one over here. It looks like it's at 1, -3. And we're going to verify that algebraically. I'm going to use the substitution method to solve this system of equations. So y equals x squared minus 4. I need some more space. I'm going to turn to the back of my paper. And my other equation is x plus y equals -2. So the substitution method means I can take x squared minus 4 and put it in place of y. I don't really need the parentheses, but when I do the substitution method, I like to start with parentheses, just so that if there's like a negative here or a number to distribute, I'll remember to do that. This is going to be a quadratic equation, so it needs to be equal to 0. I'm going to add 2 over to this side and then write this in standard form. When I add 2, that makes -2. Solving a quadratic, you can use factoring, complete the square, or quadratic formula. I like factoring, so I always try that first. This factors very nicely. And I have two solutions, x equals -2 and x equals 1. So I'm going to find the y value that goes with each of these. I can plug in x equals -2 to either equation. I'm going to use the top one simply because it's already solved for y. So in this case, y equals, this will be +4 minus 4. Remember, a negative number squared is positive. So y equals 0. That results in the coordinate point -2, 0. And here I get y equals 1 minus 4, which is -3. That results in the coordinate point 1, -3. So this system of equations has two solutions. And my graph verifies that. Next one. xy equals 4 and x squared plus y squared equals 8. These two equations form graphs that perhaps you haven't seen yet. xy equals 4 is a rational equation, and so it has horizontal and vertical asymptotes at 0, and it goes through the points 2, 2, and -2, -2, and there's a curve up here that approaches the asymptotes, and a curve down here that approaches the asymptotes. The second equation is a circle, and this happens to be standard form of a circle. So the center of the circle is 0, 0, and the radius is square root of 8, or 2√2. So it would be, the radius would be a little bit more than 2, so it would look something like this. For this system of equations, graphing is not a good method for a couple of reasons. First of all, you've probably never graphed xy equals 4 or graphed a circle before, so this would be difficult to come by. Second, my sketch here isn't very good. Looks like we're going to have two solutions if I had drawn my circle a little better, but it might be hard to figure out what those are. Might be at 2, 2, might be a little above that or below that. So we're going to use the substitution method to solve this system of equations. I'm going to take my first equation and I'm going to solve for y by dividing both sides by x. So y equals 4 over x. Then I'm going to substitute that into this equation. X squared plus 4 over x squared equals 8. And now I'm just going to multiply things out and get this in a little easier form to solve. So first I'm going to square this fraction. 4 squared is 16 over x squared equals 8. In order to get rid of the fraction, I'm going to multiply every term by x squared. So x squared times x squared is x to the 4th. X squared times 16 over x squared. This is where the x squared will cancel out and be left with 16. And then I have 8 times x squared, which is 8x squared. All right, we've got a polynomial function here, and similar to our quadratics, in order to solve it, it needs to be equal to 0. So I'm going to subtract over the 8x squared, and I'm going to factor. Now you may be saying to yourself, but I've never factored x to the 4th power, and that's okay. You can treat this as if it were x squared minus 8x plus 16. It's the same type of process. What will multiply to a positive 16 and add to a negative 8? Well, that would be -4 and -4. The only difference between what you're used to doing and our new situation is that instead of x here and here, we're going to have x squared. Now if you want to put it all together, because you've never seen this before and you're not sure this really does that, just distribute this out. So we get x to the 4th minus 4x squared minus 4x squared plus 16. And that's kind of what we started with here. It's exactly what we started with. All right, so we're factoring. Equals 0. You'll notice these two are the same. So I could write it like this if I wanted to. Hopefully you also notice that x squared minus 4 can be factored again into x minus 4, x plus 4. Excuse me, x minus 2, x plus 2. Now remember, there's 2 of these, so I'm just going to do a different kind of bracket so I don't get all confused with tons of parentheses. So you can see our solutions are x equals 2 and x equals negative 2. Now if you go back to our graph sketch, this is starting to make sense. When my x value is 2, there might be a solution up here. X value is negative 2, probably a solution down here. So in order to get the y value to go with it, I'm going to go back up to this equation, y equals 4 over x. And I'm going to substitute in positive 2. And I'm going to substitute in negative 2. So one coordinate point will be, excuse me, when x is positive 2, y is positive 2. When x is negative 2, y is negative 2. So I have 2 solutions. And if I had sketched my graph a little better, I would see that. Last one. We're going to solve this system of equations. And when you take a look at this, notice that we have the same equation here. It's another circle through 0, 0 with a radius of root 8, which is a little bit more than 2. And I will try and draw a circle there. The second equation is also a circle. We haven't worked with circles yet, but this, if I change it to standard form using completing the square, I will get a circle with an equation in this form. Don't worry about the process to go from here to here. You wouldn't need to be able to do that. I'm just showing you if we were to graph this, we would have a circle with center at 0, negative 2, coming from these two terms, and a radius of 2, 0, negative 2, radius of 2. Looks like we're going to have 2 solutions. When it comes to systems like this, where you have equations that you aren't familiar with the shape of the graph, then solving algebraically is definitely the method you're going to use. So in this case, what I would do to solve algebraically I would solve this equation for x squared. Oh, actually, there's an easier way to do this. Notice how these are all lined up. I'm going to copy this down here. X squared plus y squared equals 8. X squared plus y squared plus 4y equals 0. All my terms are nicely lined up. If I were to subtract this equation from the first one, then I would eliminate some of these terms. X squared minus x squared is 0. Y squared minus y squared is another 0. And then you can imagine another term in here. When I subtract 4y, I get negative 4y. And when I do 8 minus 0, I get 8. Now all I have to do is divide by -4 and I find out y is -2. This starts to match what this graph looks like. So in order to get the x-coordinate or coordinates to go with my y-coordinate, I'm just going to substitute this into one of these equations. It doesn't matter which one. I'm going to choose the first equation because it looks simpler than this one. So x squared plus y squared, which is -2, equals 8. Don't forget, when you square a negative, you get a positive. Subtract over 4, x squared equals 4. Now, to finish solving, we're going to take the square root of both sides. And when you take the square root of 4, remember it's going to be plus or minus root 4. So x is plus or minus 2. I have two solutions. When x is positive 2, y is -2. When x is -2, y is -2. Let's look over these examples one more time. In the first example, we could solve by graphing because we can recognize these forms. Solving algebraically, we used a substitution method. They're both equal to y, so we set them equal to each other. In the second example, we could also use graphing because we're familiar with graphing quadratics and linear functions. In order to verify what our solutions were, or are, we can use the substitution method. Solve one of the equations for y, and then substitute that into the other equation. On our third example, we have equations. We're not familiar with the shape of the graph. So, technically, we don't know this. We can use the substitution method again. Solve this equation for y, substitute that in place of y in the other equation. In the fourth example, again, we aren't familiar with graphing circles, so we wouldn't be able to come up with this. However, we can use the elimination method because our equations are lined up nicely with the matching terms or like terms. So I subtracted the second equation from the first equation. X squared minus x squared, y squared minus y squared, 0 minus 4y, 8 minus 0. And then once I have the y-coordinate, I could substitute it back in for y into one of the equations. It doesn't matter which one you use. And I can find my x-coordinates.